This is Mika Seppälä. Hello everybody. In this video I define power series and discuss the convergence of power series. I show that if a power series converges at some point x0, then it converges at any point whose absolute value is less than that of x0. This is an important result that allows us to view power series as functions defined on certain intervals. A power series P is a series of the type a0 plus a1 times x plus a2 times x squared plus and so forth. That is summation k from 0 to the infinity ak times x to the power k. In this power series, x is a variable. a0, a1, a2 and so forth are numbers. Substituting a numeric value x0 for the variable x, one gets a regular series of numbers p at x0. If this regular series converges, then we say that the power series px converges at the point x0. Consider for an example the power series p of x equals x plus 2 times x squared plus 3 times x cubed plus and so forth. That is summation k from 1 to the infinity k times x to the power k. If we substitute numeric values for x, we get ordinary series of numbers, that is infinite sums of numbers. We may study the convergence of this series by the ratio test. The quantity in the ratio test is the absolute value of the k plus first term divided by the absolute value of the kth term, and if the limit of this quantity as k goes to the infinity is less than 1, then we know that this series converges. In this case, the ratio test tells us that if limit as k goes to the infinity of the absolute value of k plus 1 times x to the power k plus 1 divided by the absolute value of k times x to the power k is less than 1, then the series converges. Now, this quantity k plus 1 times x to the power k plus 1 divided by k times x to the power k simplifies, and we get k plus 1 divided by k times the absolute value of x. The limit of this as k goes to the infinity is simply the absolute value of x. Therefore, we conclude that the power series p of x converges whenever the absolute value of x is less than 1. The following theorem says that if the power series p of x equals summation k from 0 to the infinity ak times x to the power k converges at some point x not different from 0, then it also converges at any other point s satisfying that the absolute value of s is strictly less than the absolute value of x naught. So we assume that summation k from 0 to the infinity ak times x naught to the power k converges, and that the absolute value of s is less than that of x naught. We have to show that summation k from 0 to the infinity ak times s to the power k converges. Now, to that end, we observe that since this series p converges at x naught, since the series summation k from 0 to the infinity ak times x naught to the power k converges, it means that the limit of the quantities ak times x naught to the power k must be 0 as k goes to the infinity. Therefore, after some number k1, these terms absolute value of ak times x0 to the power k become less than 1. So we can find k1 such that whenever k is larger than k1, the absolute value of ak times x0 to the power k is less than 1. Next, we use this observation to study the terms ak times s to the power k. And we first observe that ak times s to the power k can be multiplied and divided by x0 to the power k, and in that way written in an equivalent form. The absolute value of ak times s to the power k equals the absolute value of ak times x0 to the power k, and that multiplied by the absolute value of s divided by x0 raised to the power k. Now, if k is larger than k1, the absolute value of ak times x naught to the power k is less than 1. Therefore, if k is larger than k1, the absolute value of ak times s raised to the power k is less than s divided by x naught of absolute value to the power k. Now, the series formed by the terms the absolute value of s divided by x naught raised to the power k is a geometric series. The ratio of two subsequent terms of this geometric series is the absolute value of s divided by the absolute value of x naught. We assume that the absolute value of s is less than that of x naught. This means that in this geometric series summation k from k1 to the infinity, the absolute value of s divided by x naught raised to the power k, the ratio of two subsequent terms is less than 1. And this means that this geometric series converges. And now we have that the absolute value of ak times s raised to the power k is less than s divided by x naught of absolute value raised to the power k. This means that by the comparison theorem, the series summation k from k1 to the infinity, the absolute value of ak times s to the power k converges. This means that the series summation k from k1 to the infinity ak times s to the power k converges absolutely and therefore also converges in the ordinary sense. And now if we add to this convergent series the k1 terms in the beginning, so that if we start the summation from the value k equals 0 rather than k equals k1, we just add a finite number of terms. They have no effect on convergence, and therefore we conclude that since the series summation k from k1 to the infinity ak times s to the power k converges, then also the series summation k from 0 to the infinity ak times s to the power k converges as well. So we have shown that if the power series p of x equals summation k from 0 to the infinity ak times x to the power k converges at some point x naught different from 0, then it also converges at any other point s whose absolute value is less than that of x naught. Observe that the series px need not converge for x equals negative of x naught, even if it converges for x equals x naught. An example of that kind of a situation is the series px equals summation k from 1 to the infinity x to the power k divided by k. If x equals negative 1, this is the alternating series summation k from 1 to the infinity negative 1 to the power k divided by k. And this alternating series converges by the alternating series test. If x equals 1, we have the harmonic series summation k from 1 to the infinity 1 over k. And we know that the harmonic series diverges. Therefore, this particular series px summation k from 1 to the infinity x to the power k divided by k converges in the half-open interval from negative 1 to 1. Negative 1 is included in this domain where this series converges. Positive 1 is not. To summarize, we have shown in this video the following theorem. If the power series summation k from 0 to the infinity ak times x to the power k converges at some point x naught different from 0, then it converges at all points of the open interval from the negative of absolute value of x naught to the absolute value of x naught. It will converge on one endpoint of this interval, but needs not converge at the other. This power series summation k from 0 to the infinity ak x to the power k defines a function whose domain of definition includes this open interval. It may be defined also elsewhere, but from the fact that the power series converges at this one point x naught, it follows that it converges at all points of this interval and therefore defines a function.